Good morning, ladies. Calculus. Yesterday, we had a very short class where we just went over these problems. And I think Kaylee worked out problem 27, if I'm not mistaken. Was that right?
I did.
Yeah, pretty much. But it was good. We had some good discussion. So it was really a short class. Then we watched a video that had to do with kind of introduced continuity. And so...
And you talked a little bit.
Yeah, so I talked. I gave, like, I told too much of my family story, but that's just what it is. And so that was pretty much class yesterday, right? Yes. So now we are to limits and asymptotes here, and really it's vertical and horizontal asymptotes. So we're going to talk about different techniques of finding them, and I hope, especially the ones of finding vertical asymptotes, they're ones that we did, and you remember doing from pre-calculus last year. So we're going to, it says find horizontal asymptotes analytically, next note card. So we're not going to deal with this. But we have a horizontal asymptote if one or both of the following conditions exist. So now when we talk about limits, we're not talking about limits coming back to a number between, a real number between negative infinity and positive infinity. We're talking about actually going toward, all the way toward positive infinity and or towards negative infinity. And if you have a limit as x approaches infinity, and that limit is a number, that is your value of your horizontal asymptote. And also going the other direction, that is a horizontal asymptote. Usually in functions, the limits as you go towards positive infinity and negative infinity, more often than not, are the same. But sometimes they're not. So you just got to be aware of that. And we're going to be talking about finding analytically next week. That might be Betsy Bobo Botu or something like that. You heard me say that, right? So we talked about Betsy Bobo Botu. And then as far as vertical line is, you have x equals L as a vertical asymptote if the limit as x approaches L from the right, it goes to plus or minus infinity, or the limit. So these are your infinite discontinuities is what they are. That's what a vertical asymptote is, an infinite discontinuity. And then find vertical asymptotes analytically, and then we can find any holes, and we talked about holes, right? We ran into holes the last few days of class, didn't we? And then a vertical asymptote occurs if you don't have any holes. The vertical asymptote occurs where the denominator is equal to 0. And so that's one thing we did actually in pre-calculus last year, and I remember it quite well because that happens to be what the pre-calculus are doing right now. So I know what happened. So now it says for 1 through 4 below, graph and or use the table in your calculator to find A and B. And what are A and B called? The A and B are called, I circled it, but I uncircled it before I went to the next page, right? A and B are called the horizontal asymptotes, these things here, right? So now we come here and we look at 1 through 4, and so we're going to look at these, and it says you can graph and or use your table on your calculator to find these things. So I want you to go ahead and work on these things here, and we'll talk about them in a few minutes. Go ahead and work on 1 and 2, and we will talk about that. Yes, you may use your calculator for those. And eventually, I hope you'll be able to do these maybe without a calculator, but I'll just show you when it happens. Okay, what did you think for 1? You're not finished yet? We're still working on it. Okay, I will wait. I will wait.
Mr. Do you know how excited it is?
Okay. Just a minute. Okay, good. All right. So the first thing I would do on this one, number 1, now it says you can use a table view on your calculator. I want to go ahead and approach this number 1 without a calculator, in that if we can rewrite this as, I'm going to make this a skinny pen to leave myself as much room as possible. I don't have a lot of room here. So I'm going to factor out the x. So I got x times 2x squared minus 9x plus 4. And that all over x times negative 3x squared plus, in fact what I'm going to do is I'm going to factor out the negative x there. That will make my life easier, I think, maybe. So I have 3x squared minus 6x minus 24. And I see there's another thing I can factor. I can factor out a 3, right? So I'm going to put minus 3x, and I'm going to make this is what we're doing in Algebra 2 right now. Minus 2. So
Why is it that? Because they're all counted.
that's 2. And then I factor out the 3, so that's going to be 8. Okay, so what I did is I factored out x out of the numerator like this, and then I factored out negative 3x in the denominator. And so I have this left. Do you get that, how that factoring happened? I'm doing factoring like this right now in Algebra 2. Do you see, there are 2 questions I have for you. One is how I did it, and that's sort of a mechanical question. But the more important question is, why did I want to do that? Possibly to get rid of the negative. That could uncomplicate things.
It makes the more just next one.
Now, what happened is, the main reason I did this was to make these things more factorable, right? So maybe we can factor this further And we already know that we're going to have a removable discontinuity at x equals, we're going to have a removable discontinuity where x equals what number? Where x equals 0. Right, because if x is 0, we're dividing by 0, so we cross that out. And so what is that going to appear like when we graph this thing? A what? That is going to be a what? It will be a hole. That's what we found, a hole where x equals 0, because we had that removable discontinuity, removed it. And so now, I don't know how factorable it is, but let's go ahead and see if we can factor this. Probably on the denominator, we still have that -3 left, and then we have, what's this going to be here? X, what? -4, +2. Did anybody factor this thing up here though? I'm not sure if this is factorable up here. Have you tried to do that yet? So remember we did this business here with this thing, the AC here, which was 8, and this -9. So two numbers that add up to -9 but multiply together equal 8, I think. So what about -1 and -8? Is that right? -1, -8, okay.
You divide by 2 on that?
Yeah, we divide by that, Yeah.
So it would be,
So this is going to be -4.
yeah, x minus 4.
And this one's going to be 2x minus 1. And then we go ahead and bottoms up on, excuse me, actually it would be, I kind of did that in my head, it would be, I meant to say x, if you write this down as x minus 1/2 and bottoms up this guy, we're going to have 2x minus 1, right? All right, this is supposed to be 2x minus 1, not 2 minus x minus 1. There we go, 2x minus 1. So here's the 2x minus 1, and here's the x minus 4, right? So what cancels out? So what do we found here? Another hole, right? So we have holes. We have holes where x equals 0 and x equals 4. 4, right? And so where are we going to have our vertical asymptote's going to be where? At x equals, okay, we take what we have left, we set this, so we have -3 times x minus 2 is equal to 0. That's going to be our vertical asymptote. So how do we solve this equation?
Wait, what'd you do the top part?
I haven't, I'll talk about that later, but let's take care of that denominator first. Yeah, that's a good question though. We really can't do anything with that, right? Because we can't divide anything out, and so we're going to be stuck with this left. Okay, so let's talk about it. So our denominator is this thing we set equal to 0. So what is x going to be equal to? No, okay. Okay, let me show you what's happening. We got to solve for this, right? So let's divide by -3. What's 0 divided by -3?
Yeah.
0. So we have that x minus 2 is equal to 0, so x is equal to 2. So that's going to be our vertical asymptote. X is equal to 2. And so that's our vertical asymptote. These other discontinuities at 0 and 4, they are not vertical asymptote because they are, instead of vertical asymptotes, they are trying to get my t-shirts out that have all this on. Now I got too many t-shirts. Oh man. Oh, here it is. So what do you have? What do you have where x equals 0 and x equals 4? You have a hole, right? Or a point discontinuity. So you have a hole or point discontinuities at x equals 0 and at x equals 4. Why? Because we were able to remove them analytically. And then we have a vertical asymptote at x equals 2 because that was the one discontinuity we couldn't do what? We couldn't remove it. And when you graph the thing, did you see a vertical asymptote at x equals 2? Did you? Yeah, you did. Okay, so that's what it is. That's an analysis without graphing. Now it says horizontal asymptotes. We're going to go over techniques of finding horizontal asymptotes next note card. So I don't want to talk a lot about that.
Bishop, do you have a question?
What is your question?
So when you did the -3, you divided by it first. So I distributed it. Would it work on every equation? Because I know it works on this one because I got this.
Yeah. Okay. That's a good question. What happens is when you factor out a number, and leave it like this, you have a simpler form, and so this is going to be a true equation whenever this is 0. And so what it is, you can just set what's in parentheses equal to 0, and then that's an answer. That's your solution. So you don't have to worry about what's multiplied by on the outside. Okay? Because of the zero factor property, whenever this is 0, this whole thing on the left is 0. So yes, Elizabeth. Okay.
So after you take x minus 4 out of the equation,
We're left with this here, with
2x minus 1 over
-3 times that.
x plus 2. Yeah, it's a plus 2. It's a plus 2, not minus 2.
Yeah, that's a plus 2.
Yeah, but then we wrote minus 2.
Oh, did I? So I made a transcription mistake, is what you're saying.
Because
Okay.
when you graph it, the line is -2.
Okay, yeah. So I made a transcription mistake. So thanks for correcting my transcription mistake. That's okay. So therefore, that vertical asymptote is going to occur where x equals -2. Thank you for correcting me on that. You're nice about that. But that's important because there are a lot of moving parts here, aren't there? When you look at it. So what we have left, what the function is going to look like is this: 2x minus 1 over -3 x plus 2. So let's go ahead and see what that looks like. And somebody was asking me about what happens to that 2x minus 1 on top, right? So we have this 2x minus 1 on top, and we have down here this -3 times x plus 2. Is that right? And so we graph that, and if we graph this, I'm pretty sure that when you graph the original thing, you saw something that looked exactly like this, right? And so how is this different than the one you actually graphed with all the x cubed and stuff? Yeah, we're missing the discontinuities, right? at x equals 0 and at x equals 4. But other than that, it's the same thing, isn't it? Okay, so that's what we have. And so now the question is, what is the horizontal asymptote looking at this? And if we go to table view, did you go to table view and look? Anybody? If we go to table view, we go here, and the bigger we get, the more we approach. Or we can go here to ask, just to make things easier. We can just put in we can put in any number we want. So we put in ask. I'm going to put in 1,000,000 here, and we're going to see what we get. So we get negative 0.666. What's that? What is that? What's negative 0.666? What fraction is that? Negative 2/3. And so therefore, what it is, we have a horizontal asymptote it's going to be y equals negative 2/3. Okay, that was graphically using the calculator. And then we have a horizontal asymptote. We have a vertical asymptote at x equals 2. So vertical asymptote, x equals 2. And so, has anybody checked going the other way? If we put a negative infinity, let's put a negative 1,000,000. So we get same thing. Remember I told you that usually the vertical, that you only have one, and that's usually the same as you go both ways? That's an example of that, right? So, and I'm going to show you, when we get to note card 4, the Betsy Bobo Botu way of finding that out, which really makes finding a horizontal asymptote a lot faster. And I think we talked about it last year, but you may not remember that. Does anybody remember how we did this last year? No? Okay, we'll do that. We'll review that again. So a lot of moving parts to that. And so really, this 2x minus 1 somebody asked me about, that really doesn't affect what kind of vertical asymptote it is, does it? What determines what a vertical asymptote is? The denominator. Okay, very good. So that was an opening thing, that there was really a lot of things in there. What weren't there? A lot of factoring, and a lot of what I called moving parts to it. And now, this one here, for number 2, what did you end up with that? Either looking at a graphing calculator or analytically, what did you get for number 2? Did you find a horizontal asymptote or a vertical asymptote? Is there going to be a hole on this one? Why is there not going to be a hole? Can we do any cancellation of the numerator and denominator on this guy here? No, we can't. So we know that we're not going to have a removable discontinuity, but we will have, or could have, a vertical asymptote. What's going to be our vertical asymptote for this? I don't think so. 0, if we plug in 0, let me see. If we plug in 0, we would get 0, 0, negative 5. So we have a limited domain situation. But I don't think that would be an asymptote.
I don't know, when I plugged it in, it said that 0 and 1 have an error.
That 0 and 1 have an error? Okay. Yeah, 0 does, because if x is 0, what do we have here? We have undefined, right? Because we're less than, we'll have a square root of a negative number. And then you said 1 also?
Yeah.
Well, 1, if you plug in 1, you'd have 1, yeah, you'd have 4, minus 1, minus 5, yeah. That'll be an error also. So that's not like an asymptote, but that's like...
And then negative 1 came out at 0.
Okay, negative 1 came out of 0, okay. But how are we going to find, let's just put it in the calculator. 4x squared minus x minus 5. So 4x squared, square root of 4x squared minus. So 4x squared minus x minus 5. And down here, we would have 4x minus 6. Let's graph this, see what we have here. So we have, looks like we have undefined somewhere here. It looks like maybe that's a, looks like we might have a vertical asymptote here, right? And then we have, so, and do we have a horizontal asymptote? It looks like we do, right? We're going this way, that way. Pardon me? 0.5 is a horizontal asymptote? Okay, let's since Kaylee's mentioned it, let's flesh that out. So if we go to, again, we can put in, yeah, it is, because that's the new function, right? So we have 0.5 and negative 0.5, so 1/2 and negative 1/2. So we have our horizontal asymptotes. We have horizontal asymptotes. We have y equals 1/2, y equals negative 1/2. So that's it. Now how do we find what our vertical asymptote is? What do we do with this denominator to find a vertical asymptote? Okay, go back here. Let's go back to the note card, what it tells us to do, which is what we did on number 1, which is what? Where the denominator equals 0. So how do we find out what that is? Set it equal to 0. So we come here and say, okay, we say 4x minus 6 is equal to 0. So how do we solve that?
3 over 2. 3 over 2.
So x equals 3 over 2, right?
Yeah.
So what is the value of our vertical asymptote?
3 over 2.
Not 3 over 2, x equals 3 over 2. Okay? So that's our vertical asymptote, or 2 horizontal asymptotes. And when we talk about analytic, we'll be able to find these out analytically pretty easily too. Okay, the last one we're going to look at here is number 3. And so how would we do this one? What would our, did you put that in the calculator?
Yep.
Okay, good. And the horizontal asymptote you should get is y equals get y equals 0. Is that what you got for your horizontal asymptote? Emma's nodding yes. What? Okay, how did I know without putting this in a calculator that my horizontal asymptote was going to be y equals 0? How did I know that? Okay, I'll tell you why I knew that. Because what do we have up here? We have 5 minus 9x, right? And here we have 8x cubed. So what's going to happen to these numbers as they get really, really big or really, really small? Okay, well, eventually we're going to go towards 0. because these things are going to keep on getting bigger faster than these things here. So we're going to have that. So we're going to be talking about this analytical method. Okay, what about a horizontal asymptote? I mean a vertical asymptote. Find the vertical asymptote. What do we have to do to our denominator? So that equals 0. So we have 8x cubed plus 1 equals 0. So we have 8x cubed equals negative 1. So what is our answer going to be for this when we solve this? We have x cubed equals negative 1/8. And so what is x going to be equal to? Yeah, so if you cube root both sides, what is x going to be equal to? You should know what a cube root of 8 is, right? What's your cube root of 8? You should know that. 2, right? So we're going to have negative 1/2. So that's going to be our vertical asymptote. It's going to be x equals negative 1/2. And when you graph it, does it look like? Do you see that thing? Do you see it? You see the vertical asymptote negative 1/2 when you graph it? You see it, right?
We're so dumb.
Okay. Now, well, you might be rusty. I don't call you dumb. Okay. So quite a few things in this one page, right? Factoring, little solutions of things, and so here we have some notes on what they are. Limits to infinity notes.
Mr. G, do you mind going back for a second? We didn't get a copy.
Oh, okay. Yeah, I wouldn't mind. It's fine. Let's see. We're going to. We're almost out of. Well, we have less than 10 minutes of class. Okay. Okay, ready to go? Go on here. Okay. So, I'm seeing if okay. Here's from the notes here. There are only 4 possibilities for limit as x approaches infinity of f of x, or limit as x approaches negative infinity of f of x. Okay, the curve can go up forever. In that case, the limit does not exist. Here we say the limit as x approaches infinity of f of x equals infinity. And here, on the bottom it says, in this case, the limit as x approaches negative infinity of f of x equals, okay, as x approaches negative infinity, f of x approaches infinity. Remember? We did this last year. Okay. Remember this last year?
I think part of your head's chopped off.
Well, that's okay. I don't need to. Okay. We have even positive, right? The limits, negative infinity. As you go to the negative infinity, positive infinity. As you go toward positive infinity. We'll talk about the last 2 years. Okay, this one here, example 10, you say, for this one here, this curve can go down forever. In that case, the limit does not exist. For convenience, we say the limit as x approaches infinity of f of x equals negative infinity. In this case, the limit as x approaches negative infinity of f of x is positive infinity. Okay, good. So this was that odd negative we talked about, right?
Yeah.
Or no, that was this is your odd negative, right? Here's your odd positive, here's your odd negative, as you're looking at me. Okay, so we have those. And next, we go to Okay, we have some other limits here. Okay, just kind of these weird examples, but they're really instructive. Okay, it says the curve can become asymptotic to a line. In this case, the limit as x approaches infinity is a value. So in this case, the limit as x approaches infinity of f of x is, what are we approaching? We're approaching 1, right? I mean, it's the best we can tell. And down here, the limit as x approaches negative infinity of f of x is negative 1.
I'm dropping them. Mr. G, I'm going to your book.
Okay. Now, example 12. Okay. Example 12, we have the limit as x approaches infinity of f of x is, this thing looks at, so this thing is oscillating
1.
and going and going and going. So what is it going to be approaching?
0.
Approaching 0, right?
Oh, okay, Emma.
And as we go to the left, what is this thing approaching?
0.
It's approaching 0. And this is an actual type of equation. It would be like 1 over sine x or something like that. So we have those. And then we come. Okay. Now, shh, class. Okay. Then on number 4, we have something that I talked to you about. This is called Betsy Bobo Botu. Betsy Bobo Botu. And what this is I'm going to go ahead and apply Betsy Bobo Botu. And Betsy means if the powers are the same on top and bottom, then if bottom equals top, we use the coefficients. If we're bigger on bottom, then the asymptote is 0, and if we're bigger on top, we're undefined. So let's go back and look at these, and we're going to do these real fast just by looking at these ones we looked at earlier using Betsy Bobo Botu. And so here we are, and we're going to use Betsy Bobo Botu to find our horizontal asymptotes for these. So right now, this number 1 here, what do we see about the powers on top and then bottom? The highest power is what? The same, right? So what this means, when you see they're the same, we have Betsy. And Betsy means when bottom and top are equal, use coefficients.
Yeah.
So what we have is our horizontal asymptote is going to be the ratio. We're going to have 2 over negative 3. So it's going to be y equals negative 2/3. Okay?
Oh, that's good.
So that's pretty easy. Now for
Where
this,
did you get the 2 from?
Wait, it's the height.
okay, we get it from 2 here. That's our 2. There's our negative 3.
Oh, that's the same answer we just got, but we just took 20,000 steps to get to it instead of just doing. There's a little shortcut.
That's right. Betsy Bobo Botu are the analytical shortcut. So you can look at it. And I thought we talked about them in pre-calculus last year.
I think a little bit.
Because we did horizontal asymptotes
I
last
remember it
year.
now that we're doing it.
Yeah.
No.
And then for this number 3, what is this one going to be? Is this Betsy, Bobo, or Botu?
Botu.
No. Bigger on bottom.
Oh. 0.
Yeah, so 0. So what it is, this will go to 0, and so it's going to be a horizontal asymptote. It's going to be y is equal to 0. So in this case, so if you know that thing, and so what it is, these shortcuts, we're simplifying, because I've been hearing, I heard kind of mutinous murmurs in the background about dropping out. And maybe you feel that way
What are you talking
sometimes.
about?
Huh?
That's just what I heard. I just heard
No, we're
people
just
talk.
saying that we don't need a math credit.
Yeah, we don't need a math code.
I know you really don't. That's
Yeah.
true. Yeah, that is true. You
We're
don't.
just here because we love you, Mr. D.
Okay, well, that isn't one of the 4 reasons I gave you for taking calculus, but
It's
sometimes
good, right?
if it works and it helps you, then that's okay. But what happens in calculus, I can promise you this, when I took calculus for the first time, and when I retrained as a calculus teacher, there are times that I would be in the instruction, and I feel like I came out of a beating. Okay, was this one of those days that you felt like that? You felt like,
No, I'm
not
just
so much?
tired.
So you're just tired, so you don't feel like you were beaten up today? Well, sometimes you may feel that way, but just work through it, and you'll be okay. But I need to have as much as possible your good, as much attention as you can give me to detail.